Okay. So critical points for our graphs. The overall concept of critical points, those are points where the graph changes its direction or shape. Either one makes it a critical point. And then we have some subcategories of critical points. The first subcategory is extrema. Okay, that's plural for extreme. So our extremes are points where the graph changes direction. So the function has a minimum or maximum value, relative or absolute, at these points. So here my graph is increasing, it's going up the y values, and then they start to go down, so it's changing its direction. That's where that maximum is. That's what it means by change direction. Another category of critical points are points of inflection. That's where the graph changes its shape, but not its direction. Okay, so like a little wiggle. So here I'm decreasing. Here's my point of inflection because the shape changes. It's just a little wiggle, but it just continues to decrease the whole time. Okay, it doesn't change direction. It's still going in the same direction. It's just like a little bump in the road. Okay, we good? Easy enough? All right, so let's then talk about some of these relative and absolute extrema. All right, so a point with the greatest value compared to points around it. Okay, so it's not the greatest one overall, but greatest compared to points around it. You'll do a lot of stuff in calculus where you're just looking at restricted domains. You don't care about the whole thing overall. You're just looking at this little part of it. So that is called a relative maximum. Okay, relative maximum. So that's like this right here. All right, this is the greatest y value compared to all the points in its neighborhood, but not overall. Okay. No, I don't. Thank you for thank you for asking. No, I don't mean necessarily in the quadrant, and that's because it's just the neighborhood is just like literally what's right around it. Like if you were just going to take a little chunk of stuff. Does that make sense? That's a very good question, though. All right. Then if I have the point with the greatest value over the entire domain, like the greatest value overall, that would be an absolute maximum. So that would be like this one right here. It's technically, sometimes you don't know if it's a relative. Like if all you saw was that part of the graph, then you wouldn't know if it's relative or absolute. But when you have the entire thing, you know that that is definitely the absolute maximum. Okay, we good? Relative maximums can also be called local maximums, but relative is usually what you'll hear. Any questions about those? We good? Easy enough? All right. So then we have a point with the least value compared to the points around it, like in its little neighborhood again. And that is a relative minimum, like so. And then the point with the least value over the entire domain, that's going to be your absolute. And in this graph that goes with these relative maximums, the relative and absolute minimums, there is no maximum value because the y values go to infinity. Infinity is not a number. So basically there isn't an absolute maximum for that function. Does that make sense? So I don't want you to think you can't use infinity. Okay. Any questions at all? good? All right. Then let's look at some examples. So this says, give the coordinates and classify the critical points for the graph of each function. So there's 5 critical points. There's 4 extrema, relative and absolute maximums and minimums, and then a point of inflection gets you your 5th critical point. So if you look at number 1, how many critical points are there in number 1? 1, just 1. This is it, right? It's not always going to have all of them. Sometimes it'll have none of them. That's fine too. So this right here, so it says to give the coordinates. So this is at 1, 2, 3. That's at 4. 1, 2, 3, 4, 5. 4, -5. And that's a minimum, right? Is it relative or absolute? Absolute. So we can abbreviate. Absolute minimum. You can abbreviate as long as it makes sense. Don't go crazy. You can't call it an AM, all right? So on number 2, how many critical points are there? 3. See if you can find the 3. There's other points plotted, but those are just intercepts. So this is 1. This is 1, this is 1. I always suggest you mark them so you don't miss one when you're going and try and list them out. So this one here that's at -3, 1, 2, 3, 4, 5. We're at -3, 5. What is that? Absolute maximum. Then this one, which is at, and you can just write right over the graph. I know there's not a lot of room. Or maybe you have more room because you can adjust it. I don't know. It doesn't matter. That's why I try to make it light. 1, 2, 3, 4, 5. 1, -5. What's that? It's a relative minimum because it's not the smallest y value overall because this continues and so does this. So it is a minimum value, but it is a relative minimum. And then the point at 2, -3, what would that be? Relative maximum. Very good. Okay. Any questions at this point? All righty. So then when you're ready, you can move on to the next slide. In the interest of time, I think we're just going to do a lot of these together because we spent way too long out in the hallway before class. All right, how many do I have on this number 3? 2, right here and right here. So this is at -3, 1, 2, 3, 4, 5. -3, -5. That would be, it's a minimum. Is it relative or absolute? Relative, good, because this keeps on going. So this is a relative minimum. Then my point that's at -1, 1, 2, 3, 4, 5. That's a maximum, but what kind? Relative, because that keeps on going. Relative maximum. Questions? All right. How many critical points do I have on number 4? There's 3. There's 3. So there's this one and this one, but then there's also that one. Okay? So let's talk about this first one. At -2, 1, 2, 3, 4, 5, 6. At -2, 6, that's a maximum. What kind? Relative. So it's a relative maximum. Then we have a point at 0, 3. That's not a maximum or a minimum. That's where it changes its shape, where that little wiggle is. What's that called? It's what cubic functions have. Point of inflection. Very good. This is a point of inflection. point of inflection. And then we have a point at 2, 0. That's a minimum. What kind? Relative. So a relative minimum. Any questions at all over identifying those critical points? All right, you'll have some questions on Delta Math that just ask you how many there are, and then some that ask you specifically what they are. All right, so let's move on and talk about increasing and decreasing then. So moving from left to right. Moving from left to right. You always go from least to greatest. Okay? Left to right, bottom to top. Some of y'all still trying to do all the range and stuff backwards. So moving from left to right, a function may increase, decrease, or remain constant in certain intervals. So when you write this down, there's some, people can argue over how it really should be done correctly. Mathematicians don't all agree on it. So it's one of those things that it could be one way or the other. We're going to pick one way so that we're consistent and you don't get confused. And I'm choosing the way that I believe is right, but also that Mr. Ackerman believes is right. So you're consistent between courses as well. So let's say that we're trying to do increasing. Now, when you talk about increasing, when it says the function to the right, that means we're talking about the y values. Okay, what is happening to the y values as we go from left to right? So as we go from left to right, the y values are getting bigger, so it's increasing. Okay, but we write about the x values. Okay, we write intervals of the domain. The only time you put y values in your intervals is when you're talking about range. Everything else is domain. So I start out here on my x-axis at negative infinity. I increase until I get to negative 1 on the x-axis. Now, where the discussion comes in is, do we include negative 1 or do we not? Like, what's happening at negative 1? Is it increasing or is it already constant? So one school of thought is, well, that's where it's changing, so we don't include it. Okay, so it's like neither increasing or decreasing there. But you could get into philosophical arguments with people, but don't waste your time. It's not worth it. You still won't agree. All right, so then it's constant, starting here at negative 1 and going to 1, 2, 3, 4. Notice I don't care at all what the y values are. All I care about is, are they increasing, decreasing, or the same? Because I'm writing about the x values. Then it's decreasing, starting here at 4, going to infinity, not negative infinity because it's pointing that way, because I'm writing about x. Okay? What questions do you have? Yes, because we're going to not include them, because at those points, we don't know if it's increasing or decreasing or constant at that point. So everything's open for increasing and decreasing, okay? You don't even have to think about it. It's all open. All right, we good? So you can get yourself mixed up real easily because you're talking about y but writing about x. So I want you to write yourself this little note over here. So we are looking for this. We are looking for what happens to y as x increases. That's what we're looking for. That's what we're talking about. Okay? But what we write as our answer always is intervals of the domain. Okay, so we are talking about y, writing about x is basically how it works. And you might need to stop and remind yourself of that so you don't get mixed up. You don't care what the actual y values are. You only care, is it increasing, decreasing, or whatever. It's the x values that matter, because that's the domain, right? And it can get confusing because it's, but just make sure you wrap your mind back around that. All right, so let's look at number 5. I know going from left to right that my y values are decreasing right here, all the way to here. Then they start to increase, then they decrease again right here. Okay, so I'm just kind of mark it. Those are where I'm decreasing. We all agree with that? So we have to not only be able to identify it, be able to write it correctly. So it's decreasing. This is pointing to infinity, but remember, we're writing about x. So I start out here on my x-axis at negative infinity. I go until here where x is negative 2. Then I start back over where x is 1, and I go to where x is 3. You write about the domain. We're talking about the range, or talking about the y's, basically. So then it's increasing from here to here and from here to here. What is this y value? Nobody cares. Okay? Does not matter. Because, yeah, that's where I start increasing, but I talk about the x. So I start at negative 2 and go to 1. Then I union that with 3 to infinity. Not because it's pointing to infinity, but because I keep going out there that way. Everybody okay with that? Make sure you wrap your mind around that so you don't get yourself mixed up. All right, so what is not graphed on the next one, but we know is there? Asymptotes. So I always think it helps to actually draw them in so we can think through this. So when I start out here, I start out on my x-axis here at negative infinity. My y values are decreasing this whole time, all the way until it gets to whatever that x value is. So I'm starting at negative infinity, and it decreases until you get to 1, 2, 3, 4, 5, negative 5. Then I start back over on the other side of that asymptote, and guess what? My y values are still decreasing. So then it decreases from negative 5 to infinity. But at negative 5, it's not increasing or decreasing. So even though it like jumps back up there, it's still decreasing the whole time, and that's what we're looking at. Okay? Are we good? All right. So let's talk about, oh, so there's none here. So we put none here, sorry. Let's talk about positive and negative. We're not going to do this one. Move on to the next. So let's move on to number 8. Positive and negative. So give the intervals on which the function, now remember, the function means we're talking about y, and if it's positive or negative. So if my function is above the x-axis, all of the y values are positive. If my function's below the x-axis, all my y values are negative, right? We've known that forever. If my function is on the x-axis, it's 0. So this will be open as well, but for a different reason. I'm not going to include where it changes because that's at 0, and 0 is not positive or negative. So if I look at from here to here, my graph is positive. Here and here, it's negative, right? Still going from left to right, still talking about the y values, writing about the x values. So it is positive starting at 1, 2, 3, 4, negative 4 going to negative 1. So from negative 4 to negative 1, my function's positive. Not inclusive, because that would mean I include negative 4 and negative 1, and that's when y is 0. Then it's negative, talking about x, so I start way out here at negative infinity. I go to negative 4. Then I start back over at negative 1 and go to infinity. Okay. What questions do you have? All right, if you don't have any questions, you do number 9. what is the smallest y value? We don't care, okay? It doesn't matter what it is. You are not writing y values. The only time you write y values in your intervals is for range. That's it. Everything else is domain. Remind yourself of that so you're not writing the wrong numbers, okay? We good? What questions we got? All right, so after you've checked yourself with me, if you agree with everything, you can submit your notes. We're not going to do the last one. All right, and your assignment today is in Delta Math.